In this video, we go through the process of conducting a two-independent sample t-test. We'll be looking at the age of members of the Donner Party who survived versus the age of those who perished when the group was trapped in the Sierra Nevada mountains during the winter of 1846. Now, if you're not familiar with this story, the Donner Party was heading to California, but got trapped in the mountains all winter, and in some cases had to resort to fairly extreme measures in order to survive. So our research question is, are there differences in the age of survivors versus non-survivors in the Donner Party? Now, yeah, maybe this isn't the best example, but it's real data and catchy enough that I hope it will stick with you in the future. We'll assume that we're using the typical alpha of 0.05. Only 5% of the time do we want to make a type 1 error and reject the null when it's true. Only 5% of the time do we want to say, hey, look, there's the difference, when there really isn't one. And we have two samples, right? They're independent samples, meaning that the scores in one group are not in some way dependent or related to, statistically, the scores in the other group. Sample 1 consists of the members of the Donner Party who survived, and sample 2 consists of the members of the Donner Party who perished. So, based on our question, what would our hypotheses be? Now, I think it generally helps to start with the alternative hypothesis because that's what you're interested in. So, what do you think the alternative hypothesis would be? If you haven't already decided, pause for a moment and think about it and decide what you think the alternative hypothesis should be. In this case, our alternative hypothesis would be that the mean for the two populations are not equal. Notice in our question we're asking about whether there's a difference, not whether one group is greater than or less than the other. When you're looking for a difference between two groups, it's a two-tailed test because we're interested in whether either group is greater than or less than the other group. Mathematically, we write that as mu1 does not equal mu2. We could also write it as mu1 is less than or greater than mu2. Less than or greater than is just another way of saying that they're not equal. Now, also notice that we're talking about populations and mu's, not samples and x bars. Remember, we know if the sample averages are different because we can calculate them ourselves. We want to test and infer whether the mean age for the population of people in wagon trains who may get stuck in the Sierra Nevadas all winter, whether the means for the populations of those who would survive and those who don't survive are possibly different. And that's what the inferential statistics do. They allow us to infer things about populations. In this case, whether the means for the populations are different. Okay? Now, what about our null hypothesis? If the alternative is that the population means are not equal, the null is that the population means are equal. Remember, between the alternative and the null hypothesis, we have to cover all possible situations where one mean is greater than or less than or equal to the other mean. Because our alternative hypothesis is not equal, it already covers greater than or less than. So the null is just the population means are equal. Okay? Now, what about our data? The sample sizes were n equals 41 for sample 1, those who died, and n equals 48 for sample 2, the survivors. Note that the numbers may vary a bit from source to source because there's some disagreement as to who was really in the party at different points in time. But we'll go with these numbers. The mean age for those who died, sample 1, was 24.171 years, while the mean age for the survivors, sample 2, was 16.042 years. And our standard deviations for the samples were 17.415 for sample 1 and 11.756 for sample 2. Now, if you're looking at existing data, like we are here, if someone reports a measure of variability, they typically report the standard deviation. But we're going to use variances in some of the calculations, so let's just square the standard deviations to make them variances for sample 1 and the variance for sample 2. Now, as we start our calculations, for clarity, let's copy all the sample descriptive information over here in a nice column. The n, the mean, and the variance for each sample. So what was the formula that we need to do for a t-test? It's x bar 1 minus x bar 2 divided by the standard error of the difference in means. So let's plug in our means for sample 1 and sample 2, and we'll get to 24.171 minus 16.042. That gives us 8.129 divided by the standard error of the difference in means. Now, let's take a moment and think about the standard error of the difference in means. Now, we don't expect two sample averages to be exactly the same, even if the means for their populations are exactly the same. There'll always be some degree of variability, some difference just due to random chance variability in our samples. The standard error of the difference between means is how large of a difference we would randomly expect to see between two sample means if the null is true, if the population means are in fact equal. It's like the standard error of a mean, that variability we'd expect to see in means, but now it's the variability we expect to see in differences between means. Okay? Now, mathematically, the standard error of the difference between means is equal to the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. Now, why do we use a pooled standard deviation? Remember, this specific two independent sample t-test assumes the variance in the two populations are equal. And if the variances are equal, the standard deviations are equal because it's just the square root of the variance. Both of our variances are in fact estimating the same number, that same population value, but because they're based on different samples, they're inevitably at least a little different. So which one's right? Which is the correct one? Well, neither of them are. Of course, there's going to be some random variability in each of our estimates in both of those samples. So both of our variances will be off certainly by at least a little bit. So rather than pick one or the other, because the population variances for both groups are the same, we get a better estimate of the variance, that one number, if we combine the two into a single pooled estimate of the variance in the population, which we can then use as our pooled estimate for the standard deviation in the population. We then use that pooled estimate of the standard deviation to calculate our standard error of the difference in means, which again is just how large of a difference we expect to see between two sample means if the null is true and the means for the populations that those samples are drawn from are in fact equal. So if two populations have the same mean, and we take a sample from each population, the standard error of the difference in means, that thing, tells us how big of a difference we randomly expect to see between our sample averages. It's our yardstick for measuring how large our observed difference in the means really is. If our observed difference is a lot larger than that, we conclude that it's unlikely we would have observed a difference that big if the two populations in fact had the same mean. So we can reject the null and conclude that the data suggests that the means are not equal. We're just not that lucky to randomly stumble on such a large difference in means. Now, that's a lot to digest, but it will help you avoid mistakes if you understand why we're using these different estimates. Pooled variance, pooled standard deviation, the standard error of the difference in means. Okay? Now, to understand things, let's go through those calculations step by step to help bring it all together. Let's start by clearing up some of that workspace, okay? And let's move this up a bit to the top of the screen. Okay. Because the test assumes the variances for the two populations are equal, we should check that they do in fact appear close enough in size that we think it's reasonably likely that they're equal. Now, I've seen a rule of thumb that one variance should be no more than 4 times the size of the other variance, and there are analyses you can do to actually test whether the variances are different. Now, our variances are 303.282 and 138.204, so they fit within that less than 4 times the size rule. So we'll assume the variances for the two populations are equal in this case, for this specific illustration. So to calculate the standard error of the difference in means, we need to multiply the pooled standard deviation by the square root of 1 over n1 plus 1 over n2. So we need the formula for the pooled standard deviation. That's equal to the square root of n1 minus 1 times the variance of sample 1 plus n2 minus 1 times the variance in sample 2, all divided by n1 plus n2 minus 2. And again, don't forget to take the square root of all of that. Now, there are other formulas you can use. They'll give you the same answer, but I like this one because it more clearly uses the variance in n for each sample, information that's typically reported in research studies. That way, you can calculate your own t-test if you're reading a paper and you want to compare two groups that the authors may have skipped over and never compared. Okay, so let's plug in some numbers. Plugging in our values, we get the pooled standard deviation is 41 minus 1 times 303.282 plus 48 minus 1 times 138.204, all divided by 41 plus 48 minus 2. If we do everything inside that square root sign, we get the pooled standard deviation is the square root of 214.102. Phew. Now, we can pause here for just a moment, and I want to do one quick check that it's good to keep an eye on. That 214.102, that's the pooled variance. And because it's pooling the variances from sample 1 and sample 2, it should fall in between those two values. If the pooled variance is greater than both of the individual variances, or if it's less than both of those individual group variances, you know you've made a mistake somewhere. It's got to be somewhere in between. Okay? Something to check while you're doing your calculations. Don't just ignore it. Okay? But going back to our problem, remember, we want the pooled standard deviation, so we need to take the square root of the pooled variance, the square root of 214.102, which gives us 14.632. Now, just like the pooled variance, 214.202 fell in between the two sample variances. If we go back to our initial description of the samples, we see that the pooled standard deviation of 14.632 falls in between the two sample standard deviations. Again, it's a quick way to check that you haven't made an error. If the pooled standard deviation is larger than both or smaller than both, you know you've made a mistake. Don't just ignore it. Okay? I've seen students do that. Okay, let's go back now and return to calculating our t-score. We now take our pooled standard deviation of 14.632 and let's go back a few steps so that we can plug it into our standard error of the difference between means formula. Doing so, it gives us the standard error of the difference in means is equal to 14.632 times the square root of 1 over n1 plus 1 over n2. Now let's plug in our n's and we get 14.632 times the square root of 1 over 41 plus 1 over 48. 1 over 41 plus 1 over 48 is 0.0452. So the standard error of the difference in means, between means, is equal to 14.632 times the square root of 0.0452. Multiply those together and we get the standard error of the difference in means is equal to 3.112. Again, lots of steps, but it makes sense if you think about it slowly and a few times. We now plug 3.112 into our denominator for our t formula, and we get 8.129 divided by 3.112, which with a little bit of quick math gives us 2.612. Our degrees of freedom is equal to n1 plus n2 minus 2. That solves to 87 degrees of freedom for our t-test. Now, when writing our results, we put these together in the format of t with 87 degrees of freedom is equal to 2.612. Remember to include the degrees of freedom in parentheses like this, or you're not writing the answer correctly. Okay? Let's go on to get our p-value. We'll use some visual aids so it's a little clearer in terms of what exactly we're looking at. We start with our t-distribution for 87 degrees of freedom. Notice I'm going to assume that we're using my t-score Excel calculator or some other calculator, and we're not just stuck using limited options from a printed table. Here's our observed t-score with 87 degrees of freedom. Remember that was 2.612. We have a two-tailed test, so our p-value would include all the area above a t-score of 2.612. That would be this shaded area. But remember, because it's a two-tailed test, we would also have rejected the null in the other tail. So we also have to factor in a result as extreme or more extreme in the lower tail. So that would be a t-score of negative 2.612, and we need the area that's more extreme than a t-score of negative 2.612, which would be this shaded area. Now, depending on exactly how you looked up those areas, we find that the area that's more extreme than a t-score of positive 2.612 with 87 degrees of freedom is equal to 0.0053. And of course, the area that's more extreme than a t-score of negative 2.612 is also 0.0053 because the t-distribution is nice and symmetric. Our p-value reflects both of those areas, so we just add up 0.0053 plus 0.0053 to get p is equal to 0.0106. Great. Pretty straightforward. It's just like doing the z-test, except you have to remember that the exact shape of the t-distribution varies based on our degrees of freedom, so we need to use the correct t-distribution based on those degrees of freedom. Okay? Now, let's calculate our 95% confidence interval. Our formula for the 95% confidence interval is x bar 1 minus x bar 2 plus and minus that critical 95% t-score times the standard error of the difference in means. So to begin, what's x bar 1 minus x bar 2? Think about it. That's just our difference in means, which was the numerator in the formula for our t-score. If you remember, or look back a bit, it was 8.129. So we plug that in to get our 95% confidence interval is 8.129 plus and minus that 95% critical t-value times the standard error of the difference in means. So now we need the 95% critical value for our t-distribution. To see that, let's go back to our t-distribution with 87 degrees of freedom. The 95% critical value for t is that t-score that bounds 95% of the distribution, or the t-score that contains 95% of the distribution between the positive and negative values of that score. Now, if it bounds 95% of the scores, then that means 5% of the scores are more extreme than that value, split evenly between both of the tails. So we need the t-score where 2.5% are above the positive value of that score, and 2.5% are below the negative value of that score. If we look it up in the Excel t-score calculator or use some other calculator, you'll find that the 95% critical value is plus and minus a t-score of 1.988. So we plug that 1.988 into our 95% confidence interval formula, and we get 8.129 plus and minus 1.988 times the standard error of the difference in means. Okay, so what's the standard error of the difference in means? Remember, that was the denominator in our t-score formula. So it's down here, it's that 3.112. So let's plug that in and solve. The 95% confidence intervals, then 8.129 plus and minus 1.988 times 3.112. Solving that multiplication, it reduces to 8.129 plus and minus 6.186. Solve that, and we see that our 95% confidence interval ranges from 1.943 up to 14.315. This range gives us a sense of what the true difference in the age of survivors and victims would be if we had an infinite number of possible Donner Parties all getting stuck in the Sierra Nevadas during a horrible winter in the mid-1800s. In the population of wagon trains getting stuck in the snow all winter, our precise point estimate of the age difference between victims and survivors that we would expect to see is 8.129 years, with a range from 1.943 years to 14.315 years. Okay? Let's summarize our findings. Here's our initial summary of what we knew at the start of the analysis. We had our research question, our hypotheses, our samples, and the sample ends and means and variances. Our results were that we obtained a t with 87 degrees of freedom equal to 2.612. The p-value for that t-score was 0.0106, but of course it may be a little different if you were using tables and not a t-score calculator of some kind. Our point estimate for how large that age difference was is 8.129 years. And remember, we calculated that as the mean age of victims minus the mean age of survivors. So victims were on average 8.129 years older than survivors. Younger people and children survived. Our 95% confidence interval was 1.943 to 14.315 years. That gives us a sense of how precise, how accurate we think our point estimate is. This gives us a range of values where we believe the true population difference would be. Our conclusion? Well, our statistical conclusion is that we would reject the null hypothesis. Our p-value of 0.016 is less than the alpha level of 0.05. That tells us to reject the null. And notice the confidence interval does not overlap 0. We're 95% confident that the difference between victims and survivors is not 0. There is some difference, and that also tells us to reject the null hypothesis. The two agree. Our substantive conclusion is therefore that there is a difference in the mean age of Donner Party survivors and those who did not survive. All right? That takes us all the way through the steps of conducting a two-independent sample t-test. I hope you found this helpful. It is a lot of work, but you can do it. Just be careful and check your work along the way. Okay? Take care. Bye for now.